Beautiful woman. Yeah. So it's very challenging to give this talk just after a performance on Chinese dance and Chinese opera. I always believe that art is actually superior to science because it is about real creativity that comes from inside. So I'm sorry that now you will move into something a bit different. But this is again about creativity. What I will try to talk about is this world normal. So I always, starting from myself, I always had a bit of a problem with the concept of normality. When I was a teenager and then later a university student, I didn't feel normal. And I didn't want to be normal. Because normality had something to do being standard, average, or regular, or usual. And I wanted to have an extraordinary life. Okay? I wanted to be different, inspiring, inspired. Okay? So, funny is life that I found myself in Cambridge doing a PhD thesis about generalization of normality. Okay? So, as most of you here, also my first encounter with the concept of normality coded in a mathematical way. First, last year of high school, then university, where supposedly the statistical distribution gave a description of normality. Okay? So what we had here is a curve, a bell curve, where the main body, the magnitude tells you how probable that value we see in the x-axis is. And this very distribution tells us that actually most of the probability, the mass probability is in the middle, while on the tails we have very tiny, tiny probability. Okay? But what was very disturbing was that people were, my performance, my classmates' performance were measured based on this curve. Of course, we took some exams, we took some grades, but then professors, what a horrible bunch, they were trying to fit us, human beings, into these curves. Okay? And just like modern day data scientists, when their data didn't fit the model, instead of changing the model, they changed the data. That is, they changed the exam questions, they made it more difficult, or they gave grades much harsher. Okay? So that was my harsh encounter with normality. Okay? So where did it all come from, this bell curve? It's thanks to this gentleman called Carl Friedrich Gauss. Okay? At Göttingen University, he was studying the orbit of planets. This is his handwriting here. And he used a method called least squares, basically, to fit a trajectory to the movement of the planets using the data, very scarce, little amount of data he had to fit these curves. Okay? And if you looked at the distribution of the errors he made, these were the normal distribution, the bell curve. Okay? So bell curve was not up there in astronomy. It was a byproduct of his optimization criterion, which was least squares. Okay? But this thing is everywhere. It's not only about the orbit of the planets, but all the mobile phones that you use and any other telecommunication system makes the fundamental assumption that the noise here is Gaussian distributed. And all the schemes for error correcting codes, robustness, everything is based on these noise assumptions. Similarly, our cameras are also optimized for Gaussian noise. How can they, the optical receivers, function such that they are not affected by the Gaussian noise? Okay? And also the buildings that are built are tested with the assumption of Gaussian vibrations. And okay, so far so good, but what about, is there something fundamental that's supporting this? And what's supporting this is probably the most amazing, the most important theorem of probability and statistics, which is central limit theorem. So if I have random variables from very different characteristics, even from different distributions, which teach them that it has to be IID, but it's actually not true. It can be more general. And if I sum them up, I take the average, it doesn't matter how different they are, they all converge to the Gaussian one. Or if I take a die, I throw it, there are 6 options, okay? I try it hundreds of times, and I plot the histogram, I get this. If I have 2 of them, then I get this, 3 of them, 4 of them, and eventually I converge to something that looks like the normal distribution. But is it a realistic model? So what is the probability that a sample from a normal random variable deviates from the mean by 10 times standard deviation? 1.5 times 10 to the power minus 12. This is a very small number. That's really a small number. Okay? So, having said, now you must be convinced. Okay? Everything we see around should be Gaussian normal. Even my performance in random processes course should be also fitting to that normal curve. However, we can still ask, are all data distributed with the normal distribution? And nature has this terrible habit of giving answers in the harshest way. This is a picture from 1953. Probably you know Netherlands is a small country in Europe, and most of it is under the sea level. Okay? So to prevent the sea from entering the land, they have very cleverly built these barriers, sea barriers. And the Dutch engineers are very famous for this. Okay? But they made the normal assumption. And they calculated the probability that the sea waves or storm can go beyond a certain threshold, and that was minusculous, 10 to the minus 12 maybe, probability. But they are proven wrong. And this costed the lives of 2,553 people. Okay? So this is an example of a rare event which we see in the forms of storms, floods, earthquakes, financial crises, epidemics, and so on. And they're all not accounted by the normal distribution. And actually, some people warned us about this as early as 1920. The Italian mathematician Pareto, he made a model for the distribution of wealth, and he said that only 1% owns 40% of the wealth. And probably now some individuals we know very well get more than that. And 20% owns the 80% of the wealth. But if I take a daily S&P 500 data returns plot, histogram, I see that it's clearly non-Gaussian. Okay? However, this doesn't teach people any lesson, and people continue using the Black-Scholes model, which makes the Gaussian assumption. It's very good at modeling daily fluctuations in Coca-Cola price, but it's very bad at modeling economic crisis. And when the 2008 economic crisis happened, Nassim Taleb, he said that these Nobel Prize winners actually should be put into prison because they moved our attention from what is important. What's important are the crises, are the rare events that cost the life savings and the lives of ordinary people. Okay? And the second lesson we learned, you wouldn't remember this, but I was there when internet happened. Okay? And it was a big thing of losing emails. People would send you emails, you would lose them. So you would call them to say, I'm sending you an email. Can you check if it arrived or not? Okay? So that was the level. Why? Because people made the Gaussianity assumption, normal assumption. However, people from Bell Labs and Boston University, they made this observation that if I take a section here of internet traffic, open it up, then take a smaller version, open it up, and so on, you see that they all have the same characteristics because they are fractal and they are non-Gaussian, non-normal, they are heavy-tailed. So this led to the change in scheduling of packages that come from internet and change in design of buffer sizes based on realistic models. Now you don't lose any emails. An important topic for a city like Shenzhen, the underwater sensing and communications. Here, I like this example very much because my supervisor in Cambridge first alerted me of this noise type. You hear? So this is the dominant noise underwater. Can you guess what it is and what causes it? They are the shrimps that cause it. Okay? So it's clearly non-Gaussian. Okay? Well. Okay? And also dimension of Wikipedia pages, any number of words in a book, and so on. I'm finishing. Yeah. Okay. Is the central limit theorem wrong? Did we make a mistake? And making a reference to the Woody Allen film, no. But central limit theorem is an underachiever because it's very limiting. Because we always forget that it has some conditions, like small print, that we miss. It talks about finite variance. But why should we assume that the variance should be finite? Can it be infinite? And are the shrimps defying the rules of physics? Because in any physical signal, we expect finite power, finite energy. So the answer to this is that actually there's a generalized version that allows infinite variance. Whether the shrimps proved us wrong is, all the physicists wrong, is that the models we make are all for finite time, then we extend it to infinite time. Okay? But shrimps don't live infinite lives. They are born, they die very quickly, others are born, so this noise is continuous. That's why it seems like an infinite energy signal. Okay? So this wonderful distribution is called the Levy stable distribution, and this is Paul Levy from École des Mines, Paris, showed that actually there are a family of distributions with changing impulsiveness. Here are the tail details, asymmetry, dispersion, that satisfy the central limit theorem. The first person to apply this to real data, it was Benoit Mandelbrot. He applied to finance, and they changed the models overnight in 1963. Okay, back to shrimps. You can see that it provides a perfect fit. Okay, and salute to my supervisor. Okay, and this is the results of one of my master's students, and he proved that actually using this model, a derivation out of it, he can process the satellite images and uncover in very much detail the terrain characteristics from satellite images of all different frequency bands. Information is not in the normal, but in the unusual. So these distributions showed us that the tail probability is important. So the information is in the tails. So I don't care about processing the rest of the tissue. I'm interested in the cancer there. That's what I'm after. Okay? Or in ECG signals, the premature ventricular contractions can be detected from the irregularities or non-normalities. Okay? And here comes the extreme value theory, which tells us that do we have to process all the data we have? Why don't we just throw it away and concentrate on the tails of the distribution? Let's move to AI. Deep learning is what we call AI, actually. Okay? And it is a system with huge problems because, first of all, it's a deterministic system. You train it on some data, you get one result, but that's it, you get one result. It has shaky generalizations. This is how we generalize with human mind. This is what AI does or something in between. But the worst thing is that you don't know at one point it is in between. You cannot quantify your level of uncertainty. And it's not robust. So if I add only a tiny bit of noise, it can give me wrong classification results. Okay? So can we take the risk of unknown generalization of AI running a nuclear power station? So what do? First step, go random. Not deterministic, but stochastic neural networks and stochastic deep learning. So instead of these fixed weights, we will place now some distributions. But people have been doing this over the last few years. As you can imagine, again, the assumptions are normal. And these are results of two of my students, master's students who are graduated now. And they showed that actually also neural networks weights follow a Levy stable distribution. This is in log scales, that's why it looks different. This is Gaussian, this is Levy stable. Okay, finally, are the data normal? Forget about the system, let's talk about the data. So DNNs are trained on tons of millions, billions of data. That's not, actually trillions of data. Quintillions of data, okay? So we arrive now to the requirement of 10 to the 14, and it's increasing. Okay. Can we learn from extreme value theory? Do we need to train for all data samples, or should we train for rare samples only? Can we also be intelligent in the choice of data? Can we economize the size of data, the size of deep neural networks, and save time, space, and money? The implications. People are expected to behave in normal and standard ways. Education systems promote normality, not originality. And we upbring students who are good at passing exams, not in creative thinking. And, okay, let's put some needle also on us. We academicians, we scientists, we also promote normality. It's difficult to publish articles which are against mainstream thinking. I've seen it so many times. Even ideas are expected to be normal, and history is full of examples of people who have not been understood. So originality lies in the tails. We said so, right? So we should concentrate on these tails rather than the main body. But also on the negative side, it doesn't mean that people are on a simple scales. We should learn to look at it in non-isotropic ways. People can be talented in different ways, in many different ways. People can have talents, potentials in many different ways in a multiple way. So final message, do not be afraid to be in the tails of the distribution and make your lives extraordinary. Thank you.